In red, we see a brief outline of what we've done with systems of equations and matrices. There's a couple of things on here that we've done that we haven't talked about here, like the augmented matrix and row reduction. That's not necessary for what we're doing here. So the things that are necessary for what we're doing here are, number one, what it means to multiply a row and a column, which was done 9 days ago, and an assignment was due. Writing a system of equations as a matrix equation. That's what we've done right here, as a matter of fact. We did that 9 days ago. Okay. 7 days ago, then again 2 days ago, we talked about how to multiply two matrices by multiplying every possible row by every possible column, and we went over the rule for that. Went over it a week ago and reinforced it in the preceding class. Then the inverse of a 2 by 2 matrix and how to solve a matrix equation, that was done 2 days ago. On the assumption that you know the stuff that we did a week ago or more, and have done the assignment, and then that you might still be fuzzy on what we did 2 days ago, we do another example and we put a little notation around it. Okay, now here's our system. Okay, we can write this system this way, and we've seen this. We've seen how this works. If I multiply this row by this column, I get 3x minus 2y, and that will be equal to the 0. If I multiply this row by this column, I get 4x plus 5y, and that has to be equal to 23. So that the system completely represents this system of equations. Then I put some notation on it. I let A stand for the matrix. I let this x with the arrow over it stand for this column vector. And I call it a column vector. We've talked about that terminology. The column xy is going to be what we call the column vector x with the arrow over it. And the column vector 0, 23 is what we're going to call the B matrix, or the B column, or the B vector, okay, the column vector. Each column vector is just a matrix. And again, we can see how multiplying out this side gives us a matrix. It's got to be equal to this column matrix so that this product is equivalent to this system. Okay. Now, again, the system has the form A times x vector equals B vector. So I write that, A times x vector equals B vector. Then I digress over here just a little bit. Well, first I asked in class, okay, if that was an algebraic equation, what would you do to both sides in order to solve it? And somebody said, well, you divide by A. Okay, well, if these are all numbers, you could divide by A, but these are column vectors, so that doesn't quite work. There's no way to divide by a matrix, and since A stands for matrix, you can't divide by it. But you can do something equivalent. So let's go over here to the equation 5x equals 7. Now, to solve that equation, you're going to want to divide both sides by 5, and you're going to get x equals 7/5. And that's perfectly valid. That's a perfectly good way to solve this equation. But now we don't have division. So what we do have, though, is we can do inverse matrices. Okay, so instead of dividing by 5, I multiply by the multiplicative inverse of 5. Okay, well, 5 to the negative 1. And remember that we talked about negative powers on the first day of class. And you're to lock that in certain ways. And I find that that hasn't happened in most cases. So inexplicably, we're still stuck on the idea that 5 to the negative 1 is 1/5. and 5 to the negative 2 would be 1 over 5 squared, and so forth. We can't be stuck on that idea, so make yourself a note and get unstuck on that one. Okay. 5 to the negative 1 is 1/5. So that 5 to the negative 1 times 5 means 1/5 times 5. And if we multiply 1/5 by 5, I get 1. So the left-hand side, multiplying, starting the process by multiplying by the multiplicative inverse of 5, gets me down to 1x, and which is of course the same as x on this side. Now if I just do the same operations on this side, I'll have my solution. And we do get x equals 7/5. But let's see how it works out on this side. I got to do, if I do 5 inverse times this side, I'd better do 5 inverse times this side. Okay? And 5 inverse, when you're talking about numbers, multiplicative inverse, is 1/5. So I get 1/5 times 7. Okay? All the way down to here, I continue writing this 1/5 times 7. And finally at the end I relent and do that multiplication, I get 7/5. Well, you should understand every step of this. By analogy over here, we're going to multiply both sides by A inverse. Okay? Now, if you do A inverse, if you're thinking about this, you're going to want to write something like 1/3 and negative 1/2 and 1/4 and 1/5. Well, that's not A inverse. Okay? I understand why we'd want to do that. I think when I first saw this, I wanted to do that, but I quickly saw that you couldn't. Okay, whether you understand why you can't or not, I have defined, and we did this 2 days ago. Okay, so I would hope you come to class at least able to, are ready to apply this rule, and most people did. There were a couple of people who'd missed class, and you know, they had to do a little catching up. So if you're in that category watching this video, well, there's your definition. Okay? Any 2 by 2 matrix. Now this only works for 2 by 2 matrices. I made that clear last time. Doesn't work for 3 by 3s or any bigger matrices. For those matrices, you have to do something different. You have to do some row reduction in order to find an inverse. A certain matrix, you have to augment it a certain way, row reduce things to a certain goal, and you get the inverse. It's not that hard, but you got to get the row reduction process down, and unfortunately, people are finding that somewhat challenging. Okay, this doesn't involve row reduction, although this could be proved by row reduction. The inverse of a 2 by 2 matrix, well, you have to have 4 numbers in a 2 by 2 matrix, so I just call those numbers A, B, C, and D. So whatever the 4 numbers are, A is the one that goes here, B is the one that goes here, and so forth. The inverse of that matrix is, and this is a little cramped, I didn't want to take up much board space to repeat something that we'd already done. Okay, but it equals this matrix, and this matrix, as we saw before, and please review the notes from last time, we flip the main diagonal. AD becomes DA, and then we change the signs of the secondary diagonal. We put negatives on those numbers. Now, some of those numbers themselves might be negative, but you have to deal with that, and that's not difficult. People don't seem to be having a lot of trouble with that. Okay, well, it's that divided by the determinant of the original matrix. Okay, well, there's a very simple rule. If you've got it written down, you can follow it, and there's a pattern to it, so it's not too difficult. Except that maybe you don't know what the determinant of a 2 by 2 matrix is. Well, this is very fundamental, and it's very easy. Just like, you know, we looked at the main diagonal and the secondary diagonal. We did one thing to the main diagonal, we did something else to the secondary diagonal. Here, the main diagonal is AD. When we do the determinant, we just multiply those numbers. We get AD. And on the secondary diagonal, we multiply B and C. We subtract what we get on the secondary diagonal from what we have on the main diagonal. So, you have to be able to apply this rule. Then also we observe, and it's easy to prove. If you multiply this by this, you get this. And this has a name. This is called the identity. This is the identity matrix. Now, more specifically, it's the 2 by 2 identity matrix, because it's a 2 by 2 matrix. A 3 by 3 identity matrix would have similar form. ones on the diagonals, 0 everywhere else. You don't need anything bigger than 2 by 2 right now. Okay, that's okay. Now, we're going to use this inverse the same way we use 5 inverse to solve this system. We'll continue that